Okay, aldehydes and ketones are another organic functional group that you need to know about. They are separate, so there's aldehydes, and they have this carbonyl group, but they also have an H. So the functional group is the whole thing, of course. It's C double bond OH, known as an aldehyde functional group. Okay, that's that thing there, including the C. Alright. Now, if we were to name this, now in terms of aldehydes, just like carboxylic acids, the one with the double bond on it is counted as number 1, so that's 2, and that becomes ethan, and we just add al. So you add al for aldehydes. Okay, so the second one over here, we've got 1, 2, 3, 4 carbons, so that's butanal, and we've got a chlorine on the 1, 2, 3, oops, 2 is supposed to be over there, 3 carbons, so that's 3 chlorobutanol. Now ketones are a separate group. They've just got this C double bond O. It is a carbonyl group, but carbonyl groups are present in carboxylic acids and aldehydes, so that's not what we'd name it in an exam. It would be a ketone group because it's more specific, and that's always obviously got to be found. It's never going to be found on the outside, you know, the number 1 carbon on either side. It's always going to be found in somewhere within the molecule. So that's 1, 2, 3, 4, 5, or 1, 2. So we name it to give it the lowest number. So that's pentan, and that's a 2 for the position, one. So we add one as in ketone for the naming of these. This one down below has got 4 carbons in. It's 1, 2. So that becomes butan 2-one. So that's how we name them. Okay, now we're looking at physical properties of aldehydes and ketones. One of the things that's apparent is the C double bond O. Now that makes it a fairly polar molecule. Now, so if we look at this, we've got this, and that would create a significant permanent dipole, as would this, and that would mean that the boiling points and melting points of aldehydes and ketones would be higher, so it would be greater than alkanes, but it would be lower than alcohols because alcohols can hydrogen bond. Now when we look at solubility, because of this C double bond O, that creates a kind of polarity there, a dipole. That means that they would be able to dissolve or mix with water, but only up to say 3 or 4 carbons, because after that this hydrocarbon chain starts to dominate, and that would mean that any larger ketones, aldehydes, would be insoluble. So up to 4 carbons you'd expect them to be capable of dissolving, although the closer you got to 4 carbons the more difficult it would be for them. So, and that's just because of that permanent dipole, which creates some polarity. Now the reactions that you're kind of expected to already be familiar with is, for instance, a primary alcohol can be oxidized to make an aldehyde, although we have to control that reaction. So you can use a weaker oxidizing agent, for instance, but the most significant thing is you need to distill off the aldehyde as it forms. The aldehyde will have a lower boiling point than the alcohol or the carboxylic acid that could potentially form, and this would come across first, so you distill off the aldehyde as it formed. Now secondary alcohols can be used to make ketones, so, and that's the double bond there, and these are reactions that you should already know. Now the other reactions of aldehydes are more interesting. Okay, now one reaction again you're expected to know is, if you know that a primary alcohol can go to an aldehyde, then the aldehyde, if it's oxidized further, either by something like dichromate, which goes from orange to green, or permanganate, which goes from purple to colourless, will form the carboxylic acid, so that'll be from ethanol to ethanoic acid. Okay, so you expect to know that. Now, that oxidizes fairly easily. In fact, that's the distinguishing feature about aldehydes. Now, because both an aldehyde can be oxidized in this way, as well as a primary alcohol, there are some other reactions that may be of interest. The silver mirror one, for instance, which effectively has silver going from a iron to a solid if we're doing the redox reaction, and that forms a silver mirror. Now Tollens reagent itself has ammonia complexed around it, and so we could still do this and just balance it this way. We'd have plus 2 NH3. Now that is in basic conditions, so the aldehyde, if it was, oops, I'm making a acid there, when that reacts, we'd expect it to make carboxylic acid. But if it's in basic conditions, this carboxylic acid is actually going to react with the base, and that H is going to go over there, and we're going to end up with the conjugate base. So this is basic conditions, and we can tell that because of the NH3. But the key thing in this, actually, because this is more excellence understanding here to know what happens, is just to understand that a test for aldehydes is a silver mirror test, which is what this is. And sometimes you get a black precipitate instead, but an alcohol cannot be oxidized in this way. Tollens reagent is too weak to do it. So if we had to tell the difference between a primary alcohol and an aldehyde, Tollens reagent would do it because it would stay colorless. If it was negative, so it would stay that way with an alcohol, but it would change to being a silver mirror on a glass surface in the test tube, for instance, if it was positive. Now the next is Fehling's and Benedict's. Now they are separate tests. One has copper 2 plus in a complex with citrate and the other with tartate. Essentially though, all you need to know is that if you use either of these, it's going to start off blue, and if it's positive, it goes to brick red. And effectively that's going from copper 2 plus to copper 1 plus. So if you were to balance this, just remember that you'd have to put 2 here because there's a 2 over there. That's in a redox balancing, but to the most part you just need to know the observations, which is Fehling's will go from blue to brick red when positive, but you should also say what happens when nothing happens, and not just say nothing happens, but say that the solution would remain blue, and that would show that there was not an aldehyde. So this again could be used for testing, say, a ketone, which doesn't react with Fehling's or Benedict's, and it would stay blue, whereas an aldehyde would change. Okay, and ketones, the main thing is really their unreactivity. They cannot be oxidized, so they generally have no reactions. Okay, well, at least in year 13 we don't talk about them. Okay, so those are the main things. It's really about the ease at which aldehydes are oxidized. So Fehling's and Benedict's, which goes from blue to that kind of brick red color, and silver mirror test, which forms on the test tube or beaker or whatever you're using, whereas a primary alcohol will not do that. Okay, and that's aldehydes and ketones.